Hi, we're going to make the switch from proportions to averages today, and we're going to create confidence intervals and look at hypothesis tests for figuring out what's going on with things with units and what happens for things on average. So I have two small little sets here, the numbers 2, 5, and 8, and I'm supposing they show up 1/3 of the time. Just as a warm-up for myself, I'm reminding myself how to find an average. To find an average, I add these three numbers up. I have 2 plus 5, 7. 7 plus 8, 15. Divide by the number of terms. I have 15 divided by 3. I have an average of 5. Standard deviation is the average gap size. I can see I have a gap from 2 to 5 of 3, and I have a gap from 5 to 8 of also 3. So my average gap size, or my standard deviation, is 3. When working with the population, I had slightly different formulas here. To find the average, I take the first x value times the first probability, and I add all of those things up. So I would have 2 times 1/3 plus 5 times 1/3 plus 8 times 1/3. And when I do that, I end up getting an average of 5, because in both of these, 5 is very clearly the middle or the average. The standard deviation I find by taking the square root of, I'm going to take the first value minus the center squared times the probability, and then I'm going to add all those things up. So the first value in my list is 2. The average is 5. 2 showed up 1/3 of the time. Next value I have in here is 5. I'm going to have 5 minus 5. That's just 0, so this next part's just 0. Last part I have, next value is 8. Minus the center is 5. Squared times the probability for 8 is 1/3. I'm going through this somewhat quickly. This is in those 243 completed notes if this is something you need to review. This is coming from lessons 2 and lessons 5 of those completed notes. I'm happy to answer any questions you have on these things. It's more important what the results are than how I find these things. So for now, just compare the two things. They have the same average. I'm typing this into my calculator to get a standard deviation. And when I do so, I get a standard deviation of 2.449. So just as a quick note here, before I try to do anything with today's lesson, it looks like my sample average, x bar, is really, really close to my population average. In a lot of ways, this makes sense. So if I go out and I measure 6,000 frogs, and I find that they have an average weight of 1 ounce, I would expect the average weight of all frogs to be really close to 1 ounce. I expect that my sample average for really large samples looks a lot like my population average. Unfortunately, I can't say the same thing here for the standard deviation. I had a standard deviation of 3, and 3 is not the same thing as 2.449. In other words, if someone promised you $300 and you only got paid $245, you'd be short like 55 bucks. You'd probably be pretty pissed off about that. So X bar and mu, these are interchangeable symbols. They're really close. S and sigma, not so much. This will be much more important for what we're doing later on. Just treat this as a quick review of some 243 stuff before we get in the middle of it. Okay, I'm going to take a couple of pieces. I'm going to pull these things together, and then we're going to look at a ton of examples so we can figure out exactly what's going on here. So the central limit theorem, this was the model that allowed me to compare sample averages and population averages. And I'm seeing part of this top activity showing up again. I expect my sample average to look like my population average mu. The way that this varies by is by sigma over the square root of n. As with pretty much anything we do, there are going to be several assumptions for using this. Random, independence within your sample. The backup for this is sampling less than 10% of the population. And finally, a large sample size. I don't have a p in this per se, so I can't really do n times p. So instead, I say I need to have at least 30 samples, or my distribution starts looking like a normal curve. What I mean by this is if I graphed my starting distribution for like weight of frogs, and it looked something like this, where it looked like a bell curve, I would say, yeah, that looks great. If I looked at my original distribution for weight of frogs, and there were a lot of really light frogs, but there were a couple of more Rubenesque frogs, where it had sort of this right-tailed thing going on, I would not call that large N. It does not start out normal enough. I would need to have at least 30 samples to get over the fact that it starts out so skewed. So this was the model for comparing averages. Reminder, when I'm working with confidence intervals, I take the center of my distribution plus or minus whatever distribution I'm working with stars, so for example, Z stars, multiplied by my standard deviation thing, my standard error. And all confidence intervals do the same thing. They go from the sample, so this is going to start at my sample average x bar, and it's going to go to the population. It's going to tell me what I should expect for my overall average mu. So this is an extremely useful thing if I can figure out how this works, because this means I can sample like 100 households in Beaverton and ask them, hey, what's your average salary? And I can then figure out what the average salary is for all of Beaverton just based off of those 100 individuals. So I can take a small amount of information and extrapolate that considerably. I can look at the average temperature of 30 people and figure out the average temperature for everyone. I can look at the average height of a collection of 70 people, and I can extrapolate and figure out what the average height should be for an entire region of people. So using a small amount of information, I'm going to figure out what happens for a population. So this model here, this is based off samples. So in order to come up with my confidence intervals for averages, I'm going to take my model up here. I'm just going to kind of plug things in here if they're based off of a sample. So just highlighting stuff up above, X bar, this is the name of the distribution. It reminds me that I'm working with averages. And tells me how to draw the curve. This is the normal distribution. I use z-scores when I'm using the normal distribution. This mu, if I was drawing the curve out, mu is what I'm expecting. That is my center. And this sigma over the square root of n, that's my standard deviation. It's how things vary. So my distribution here is this normal distribution. And I use z-scores when I'm looking at the normal distribution. So I'm going to take this model that I have above, and I'm going to make this based off of samples, assuming I can make those switches as I go along. Let me show you what I mean by that. So here I had a center of mu. So I'm going to put that center down here, but I have to make it based off of a sample. Population average is mu, sample average is x bar. So my center is x bar. And I can do this because mu and x bar, these look the same. My average for my sample, 5, was the same as my average for the population, also 5. So I'm interchanging mu and x bar, and I don't feel bad about that. I'm working with the normal distribution, so I'm going to be using z-scores. What I would like to do here is I'd like to change the sigma to an s, and I'm going to do so for just a second, over the square root of m. So this is what it would look like if I could switch x bar and mu. I can, no problem, those look the same. And if I could switch sigma and s. And there I feel a little bit more uncomfortable, because up here I had a standard deviation of 3 and a different standard deviation of like 2.45. These are not the same number. I can't interchange these things. I can't just say that sigma looks like S. So even though I really want to do this, I cannot say x bar plus or minus z star S over the square root of n, which is a massive bummer because this would give me my confidence interval formula. I would just be able to plug in my numbers, my average, my standard deviation, my z star, and my n, and it would immediately give me my confidence intervals. This would be a much easier formula to use than even my proportion model. So this would have been our fastest model yet. So it's a little bit too bad that doesn't work out. The issue is I can't write S there. I'm stuck leaving that thing as a sigma. So my formula looks like x bar plus or minus z star sigma over the square root of n. So if I want to know what the population average is, unfortunately, I need to know the population standard deviation. But I can only find the population standard deviation if I know the population average. So this might be true, but this is also the most useless formula I could possibly have. The person that first discovered how useless this was a mathematician named Gossett, and he worked for the Guinness Brewing Company. And what he noticed was the amount of variation that the formulas were telling him was not the same as the amount of variations that he was anticipating. And as a result of this, they had to do additional samples to figure out how much things really varied. What was the downside of this? All of those samples cost beer. And Gossett really didn't want to see a loss of beer. That was something important to him. So he created an entirely new model and he named it student distribution. So this model fixes this sigma to S switch. And I'm going to give you all the properties of this t distribution, and it's going to look a lot like the normal distribution. So in the back of your head, think, okay, I might be learning a new model here today, but it's really just like the normal distribution. And here's what he noticed. Gossett noticed that the sample average followed a t distribution with the center of mu and a standard deviation of S over the square root of n. So I can switch sigma for S and write an S here now. And when I do that, I no longer use z-scores, I use something called t-scores. This will be based off of something called degrees of freedom. We'll circle back to this. But what this means is my formula that used to look like x bar plus or minus z star sigma over the square root of n, where I didn't want to have the sigma. Well, I could change the sigma to an S. If I change this to an S, I change this z to a t. And this might just seem like alphabet soup here for a while, and that's okay. We're going to do some problems to make this a bit more concrete. But the assumptions for this model shouldn't be too surprising. Random, by that I mean there's no bias. I need to have independence. By that I mean that one sample does not affect another, or I'm sampling less than 10% of the population. And I need a large sample size. When I say large sample size, I still mean 30 or more samples, or it starts normal. So however this t distribution works, it's sort of like this magic cure-all that allows me to use pretty much the same setup. I have my average plus or minus my critical value times my standard error. And Gossett, for this student t distribution, he discovered that the amount that you need to fix really depends on the number of samples. If you only have 3 samples, you have a lot of error for your approximations. If you had like 1,000 samples, you had considerably less error. That error depended on how much freedom you had. So degree of freedom, this is the number of things or number of values you need to know everything. And I abbreviate degrees of freedom as lowercase df. That's why I keep writing df here. That stands for degree of freedom. So as a quick example, let's say I have two categories. So I have n equals two categories, heads and tails. And suppose that I tell you in total there were 50 flips. And I want to figure out how many of these categories do I need to know in order to know everything. So a priori, I'm not sure how many heads I would get in 50 flips. Like maybe it's 25, but I could get 27. I could get even 20 heads in 50 flips. This number can change considerably. So I have two categories. I don't have enough to figure out the number of heads, so I'm going to fill in a number. Let's say I get 22 heads. What I want to know now is, based off this one category, do I have enough to figure out the second category? And I'm going to give you a second to see if you can figure that out on your own. Do I have enough to figure out the number of tails? And hopefully you figured out, well, yeah, of course I have enough to figure out the number of tails. If this is out of 50, I do 50 take away 22, I had 28 tails remaining. So in order to figure out what was going on for both of these categories, I needed to be told one of the two categories. So in order to know two things in total, you have to give me at least one piece of information to start out with. Let's look at another example. Let's suppose I have categories 1 through 6. I'm looking at a die. And let's suppose in total, I have 100 rolls of this die. So I'm starting with n equals 6 categories, and I want to know how many of these categories do I need in order to solve for all of the categories. If you're following along at home, try pausing the video and seeing if you can figure this out on your own. I'll still give you some spots as we're going through the problem together to pause as well if you'd like a second or even third try at it. Okay. So I don't know how many ones I have. I'm just going to go through this one category at a time. And I'm going to just make up a number. Suppose I got 20 ones. Do you now have enough to solve for the rest of the categories? If so, go for it. If not, how many categories in total am I going to need to know in order to solve for everything? So again, if you're at home, try pausing the video and figuring out the number of categories out of 6 that I need to know in order to know everything. So 20 for the first. I'm going to give you the second one. Let's suppose this is a 0. I don't have enough for the rest, so I'm going to give you another one. 15. I'm up to 35 out of the 100 values. There's still 65 values I don't know. Number of 4s. Let's suppose this is also 15. I'm up to 50 so far. I'm getting a little bit concerned because I have to know almost everything to solve for these categories. So I have 50, but I still don't know what the split is for these last two. Let's suppose I have 30 here. Well, now running total 20, 35, 50, 80. I finally have enough to say if I have 80 so far, I must have 20 left over. So in order to know all 6 things, someone needed to tell me at least 5 of those, degree of freedom of 5, in order to solve for the missing 1. Let's suppose you have 1,000 categories, and I'm not going to write that down, I'm not that crazy. I want to see if you can figure out how many of those 1,000 categories I would have to tell you in order to solve for all of those category values. If you're doing it at home, try pausing the video and see what you come up with. Okay, if you're kind of watching and seeing what happens, if I knew 1, I can solve for the 2. If I knew 5, I could solve for the 6. I always need to know pretty much everything, unfortunately, except I can always solve for that last category. So if I knew all but one of these categories, I could solve for the remaining one. So in other words, I need to know 999. I need to know all but one category in order to solve for the remaining values. So what do you think this means if I start out with n distinct categories, or n values? I want you to see if you could come up with a formula there. So pause the video, look at the relationship between these. What do you think the degree of freedom formula looks like in general? For me, it looks like 2 to 1, 6 to 5, 1,000 to 999. I'm going down by 1, so my degree of freedom formula is always 1 less than the number of samples. So when I'm writing down these formulas and I'm saying it's based off the degree of freedom, my degree of freedom is n minus 1. And I said these curves depended on that degree of freedom. Let me show you what I mean by that. So I have on this page a whole bunch of curves drawn that look really similar to one another. So this dotted line, this ends up being a t-distribution with a degree of freedom of 1. And if you look at this and you thought, well, that just looked like the normal distribution. It almost is the normal distribution. T-distributions look like squished normal distributions. They're a little bit shorter, they're a little bit squattier. It's just like you took a normal distribution and just pushed down on it a little bit more. They vary more. So if you have a small number of samples, it looks like a normal distribution, but it has more variation to the curve. This is for a degree of freedom of 1. This is also a t-distribution, but this is for a degree of freedom of 12. So as you sample more and more, eventually, this thing's going to look like and I'm drawing that to the best of my ability there. This red curve is the actual normal distribution. So as I sample more and more, this t-distribution, the short squatty thing, is going to grow into that normal curve almost perfectly. So the question might be, well, how do I look up all these t stars to get my confidence intervals? Because my intervals are supposed to be my center, x bar, plus or minus my distribution. I'm being told that it's these t-scores, times my standard error. That was sigma over the square root of n for the central limit theorem. But I'm using samples, I'm using s. Previously, we used these normal distribution tables. And to find the t star for 90%, I found the size of the one tail and I looked it up. Here's the problem. I would have to have a different one of these tables for every single degree of freedom possible. So I would have a table for a degree of freedom of 1, I'd have a different table for a degree of freedom of 2, and so on. So I would have thousands and thousands of these tables to work with in order to find all these critical values. Luckily, we have another thing that we can use, and I'm going to change my screen here, and I'm going to show you what that looks like and where to find it. So I am inside of my D2L page here, and I am in tables, and I've pulled up something called a t-table. And here's how this t-table works. This first column here is my degree of freedom. That's my n minus 1 number. And the number down here at the bottom, this is how confident I want to be. This thing is a grid, so wherever these things meet up, that is my critical value. So for example, we're going to do one of these things together. So I'm going to try to put these things side by side. And switch the camera so we can actually see. Perfect. So for this one, I want to find T star if I want to be 90% confident and I have 16 samples. So here's what I'm going to do. I am going to find 90% in the center. And if I have 16 samples, my degree of freedom is going to be 16 minus 1. I'm going to have 15 as my row. So I'm going to go to the 15 degree of freedom row, meets the 90 column, and whatever number is sitting there will be my T star. I'm going to give it a go. So I'm going to switch back over here to my T table. And I am in the 90 column. I got to go to the bottom on this thing to find that 90. Great, so that's the second column. And it wanted me to have a degree of freedom of 15, which gives me this right here as my critical value. My T star is 1.753. I want you to, I'm going to return the packet to you. And it always wants to show my face a second or third time. That's really kind of them, but I don't want that. I want you to find T star for all of these different problems, assuming I have an N of 51, an N of 500, an N of 30, an N of, say, 10,000. Now, just as a note, if this falls between two different values in your table, you probably want to take whichever thing it's closer to. I personally err on the side of I always assume I have less control instead of more control. So if it's between 20 and 40 and it's considerably closer to the 20, I'd assume 20. If it was halfway between 20 and 40, I can either average them out or use the value for 20. So for this next one, I want you to go to the 95 column, and I want to see where that meets a degree of freedom of 50. So on each of these, as a first step, subtract 1 to get that DF, and then find where that degree of freedom meets your confidence. I'm going to ask that if you're following along at home, you pause the video and try to find these values. I'm going to list these out as well for myself just to see what I get. So when I did these, to double check your work, if I was trying to find T star and I was my critical value and I started with 51 values, this gave me a degree of freedom of 50. That ended up giving me 2.009 or so. 50 met the 95. For this next one, I ended up with a degree of freedom of 499. That was super close to 500. So when I looked this up in my table, I just used the value for 500 to get a critical value of 2.588 or so. Next one, 92. 92 wasn't in my table, but I had 90 and 95, so I just averaged those out. So my degree of freedom was 29. My T star for 29, when I averaged them out, I got something like 1.872. For this last one, 10,000, this was massive. I'm going to pull up that table and show you how big that was. So my degree of freedom was 9,999. So I'm going to pull up that table again. And I'm going to try to find 9,999 and I have a little bit of a hard time because it stops at 1,000. So it's even bigger than this. But do you notice how close all of these values are getting on the bottom? So I may as well pretend that I have like almost an infinite number of values if I have something so large as 9,999. I'm going to look this up for 99%. This gives me a T star of, oh man, that looks super familiar. A T star of 2.576. And I think I've seen that before because in the back of my head, I have the numbers 1.645, 1.96, and 2.576 kind of rattling around there. And I'm noticing 1.645 for 90%, 1.96 for 95, 2.576 for 99%. When I'm looking at this infinity row here, this is really my z-scores that I'm seeing. So this starts out as just a t distribution, but as you sample more and more, these t-scores start to look like z-scores. They start out a lot larger. They start out kind of squatty at 3 and 12, but given time, that 3 matures into the proper value, that 12 matures into that proper value. So this distribution assumes that you have a lot of error for small samples and that you have reasonably precise values when you're working with larger samples. It corrects as you go along. It might feel like a lot, so we're just going to take all the pieces and put it together here. I'm going to switch the screen back to the packet. When I do this, you might end up seeing my face 2 or 3 times. That is either a bonus or not a bonus, depending on your opinion. Great. Observation for large n. T looks like Z. So we might have a new distribution, but they're going to work exactly the same way. So when I found z-scores, I used to do like value minus center over standard deviation. Well, if I'm ever asked to find a t-score, I'm going to find it by taking value minus center over standard deviation. It's actually exactly the same formula. So I cannot tell the difference when it comes to these equations of z-scores and t-scores. The only difference is I end up with slightly larger numbers that I'm multiplying by when I'm trying to find that margin of error. So let's look at an example of this thing from start to finish. And this is just another picture of showing you that if I start with a small degree of freedom, say 10, and I sample enough times, say 1,000, eventually this becomes that normal distribution. So it's just another picture highlighting that same relationship. But the big takeaway is if I want to use S instead, I can use T star to correct for using S. So here's an example. Suppose that I am given an average of 18 inches. Maybe this is like the size of trout in a river. And those vary by 20 inches. Whoa. And I have an N of 31. So one good news is 31, I'm loving that. I'm starting with more than 30 samples. I can assume I'm working with a normal distribution. It says create a 90% confidence interval. So I'm going to do just the tiniest amount of scratch work to start this problem off, and then we're going to get right into it and be done almost as soon as we start. So here's my tiny amount of scratch work. If I have 31 samples, my degree of freedom is 30. So I want to find my critical value before I start this thing out, and then smooth sailing. So I'm going to go back to that table. I like to think that I'm getting faster at switching between the two as I practice. It's a learned skill. Degree of freedom of 30. And I want it to be 90% confident, so I'm going to the 90% column here. I see where these things meet up. I see the number 1.697. So I'm going to go back to my packet here. So 1.697. And I'm using 1.697 here. And just as a note, if we used to use these scores, a z-score would have been 1.645. So the values are just like a tiny bit larger than if I'm working with the normal distribution. But it's going to look almost the same, where I'm taking the center, or my average, plus or minus whatever distribution I'm working with, times my standard error. So my center is my average. My distribution, I'm using t-scores with 30 degrees of freedom. And my standard deviation is my s over my square root of the n. Average. Well, I had an average of 18 inches, plus or minus. My critical value was for 30 was 1.697. It said a standard deviation of 20 inches and number of samples 31. I'm going to type this into my calculator, once with the plus, once with the minus, and then I'm going to be immediately done with this formula super fast. On the low end, I have 18 minus 1.697 times 20 divided by the square root of 31. When I type this into my calculator, I got 11.90. These have units, unlike the other ones that were just percentages, inches. Changing that minus to a plus, I get 24.10 inches. So my sentence that would go along with this would look like the following. We are 90% confident that the interval of low end 11.90 inches to high end 24.10 inches includes the population or the true average mu. So if this was trout in a river, based off of these 31 trout for the length, I've made a conclusion about what should be going on with all trout in that lake or river with 90% confidence. I want to do another one. Dream job here. Miss Worry weighs 100 cats and finds they have an average weight of 8.5 pounds with a standard deviation of 1.8 pounds. Assuming that the sample is representative, create a 95% confidence interval for mu. Now here's why I might say this sample is representative. That would mean that there's no bias. So if I'm checking my assumptions, random, I feel pretty good about this. It says it's representative. Independents are 10%. Well, I probably have both. Weight of one cat does not affect another. It's not like cats sympathy eat. If one cat starts eating a lot, it's not like another cat starts eating a lot, unless they live at the same house, I guess. But even in that situation, I have 100 cats, and that's way less than 10% of cats. So even if you think, well, what happens if you end up with 2 neurotic cats like I have? Probably not included in that representative sample of 100. And finally, large N. Well, in this case, it says I am dealing with 100 samples. 100 is bigger than 30, so I'm feeling great about that. I passed the assumptions. I'm good to go to finding my interval by taking my average, my critical value, times my standard error. Just as before, all of my vocab stays the same, so if this asked me about the center, I would still call this thing the center. If a problem said, what is the margin of error? The margin of error is forever and always the thing after the plus or minus, so my mo or margin of error is this piece. What I would like you to do if you're following along at home is pause the video and see if you can figure out what X bar, S, and N are. You can get that just from reading the problem. And then go to that T table and see if you can find T star for whatever my degree of freedom should be. Keep in mind I'm working with 100 samples. So go ahead and pause the video, try that out, see what you can come up with. So when I did this on my own, I had an average of 8.5. Units are pounds, so I am going to write myself a note because if you're like me, I tend to get going through the problems pretty quickly and I get to the bottom and I forget to include my units, so I'm just writing myself a note at the start. average of 8.5, standard deviation of 1.8, sample of 100. I've plugged in my X bar, S, and N. Nice and easy. They gave me that info. Last piece, T star. Well, if I have 100 samples, my degree of freedom is 99. So in my table, I'm going to go to that 99. I don't have a 99 row. I have a 100 row. That's really close. I'll use that. Meets the 95 column. And when I do that, I got a critical value of approximately 1.984 or so. Please double check my work on that 1.984 to make sure you're getting the same critical value. I'm going to do this once with the plus and once with the minus. I'm going to type in everything after the plus or minus this time to make my life a little bit easier. So I'm typing in that 1.984 times 1.8 divided by square root of 100. I'll show you what I'm doing, but I'm not doing anything special. And it might not even show up that well. It doesn't even show up that well. But when I typed this into my calculator, the amount that I was adding and subtracting was 0.357. So I anticipate cats have an average weight of 8.5 pounds, give or take 0.357 pounds. So this is my estimate, and that's how much it should vary. That's my margin of error. On the low end, I get 8.143 pounds. And on the high end, when I do the same thing with the plus, I end up with 8.857 units, also pounds. So my sentence that would go along with this would look like, we are 95% confident that the average weight of cats is between 8.143 to 8.857 units pounds. I've now made a conclusion about all cats in the world based off of only 100. I'm going to do one more example with you. This example is not in your packet, but it's going to be using some raw data because I want to show you how you can double check and do some of these problems on your own if you have some messier data sets. So I'm going to assume that I'm still working with weight of cats, but I'm going to flip the page over and I'm just going to give you a sample of some made up weights for some cats. So create a 95% confidence interval for the average weight of cats if I have a sample and I weigh some cats and I find one weighs 8 pounds, another cat weighs 10 pounds, another cat weighs 10 pounds, and I have another cat coming in at 12 pounds. So my formula that I need is X bar plus or minus T star S over the square root of N. I can find the average, I can find the standard deviation, I can find the number of samples, I can calculate my critical value, and then I'm good to go. So let's make a note here. Suppose the weight of cats is normally distributed. And I want you to try to figure out why that last part is important. Why would it be important to have the weights of cat be normally distributed? So pause the video there. This is the one assumption that I think needed to have this extra piece of information in order to be okay. So my three assumptions: random, let's suppose these cats were randomly sampled. Independence, well, the weight of one cat should not affect the weight of another. Let's assume that the units here for this problem, I'm working with lbs. Last assumption, large N. Well, the quick check, 1, 2, 3, 4 makes me feel pretty nervous because N equals 4 is less than 30. But if it tells me the weights are normally distributed to begin with, then for large N, I would still feel okay because it starts normal. So unless it tells me something about starting normal, or unless it gives me a graph of what the weights of cats look like, and I see that it looks like this bell curve, I can't pass this large N assumption. Luckily, I'm told it starts normal here. This doesn't help me out with the calculations, but let's do that. I'm going to start by finding the average. To find the average, I take the weights of those cats, 8, 10, 10, and 12. I add up the values, and I divide by the number of terms. I think you'll find when I'm doing this problem that I'm doing way more work for just the setup for finding these initial values than I am actually for the formula. The formula, I just plug in 4 numbers and I'm done almost immediately. I don't know what this average is, but when I type that in, this gives me a total of 40 divided by 4. This gives me an average of 10. I'm halfway there. So the next thing I'm going to do is find the variance using the variance formula. I'm reviewing some 243 stuff here for you. And then I'm going to use that variance to end up with the standard deviation. The formula for the variance, in case you forgot it, this is why I want to do this example with you, is I take the first value in the list, I subtract the average that I just found, and I square it so I don't get 0. I add all of these things up. Next value minus the center squared, next value minus the center squared. I'm doing this so I don't end up with negatives, otherwise things will cancel out on me. And I divide this by the number of gaps. If I have 5 values, the standard deviation divides by the space between, so 5 values is 4 gaps. If I have n values, I have n minus 1 gaps. If this n minus 1 looks familiar, it should. When you're finding the variance, you always end up dividing by the degree of freedom on the bottom. Let's see what that looks like for this problem. First value in my list was 8, and I can actually see my list here. My list is 8, 10, 10, and 12, so I'm just going to use those numbers. Minus the average was 10. If I did this, I got a -2. I'm talking about spread. It doesn't make sense to say I'm -2 away. So I'm going to square that so I don't say I'm -2 away. The next value in my list is 10. Minus the average is 10, that's 0 squared. These are nice numbers, I'm liking this example a lot. 10 minus 10 again, that's another 0. 12 minus 10, last value in the list squared. I have 1, 2, 3, 4 values, spaces between. I have 1, 2, 3 spaces between, or 3 gaps. Doing a little bit of mental math. This is -2 squared, so that's 4. So I have 4 plus 0 plus 0. 12 minus 10 is 2. 2 squared is 4, so I have 4 plus 0 plus 0 plus 4. I'm at 8. If I do 8 divided by 3, I end up getting 2.66 repeating as my variance. To get my standard deviation, I take the square root of that variance. The square root of that 2.66 repeating gave me 1.633 or so. Whew. Average of 10, standard deviation of 1.633, number of values 4. I've got all the pieces I need for my interval, because that interval formula again was x bar plus or minus t star, whatever my degree of freedom is, s over the square root of n. My average was 10. Ooh, critical value. I'll come back to that. My standard deviation S was 1.633, and I'm working with 4 samples. I'm anticipating a really large margin of error here because if I only have 4 samples, I'm going to have a considerable amount of error. So I'm not going to be surprised if I have a large critical value and as a result of that, a really large MO. But let's try to find that out. If I have 4 samples, I should have a degree of freedom of 3. So I'm going to go to my table and I'm going to find where the 95% column meets that degree of freedom of 3, and I'm going to plug it in right here. So for the last time here today, I'm going to go into that t-table. Degree of freedom of 3. I want to be in the 95, that's the middle column. These meet, whoa, so usually for 95%, it's 1.96 or about 2-ish. This is way bigger at 3.182. So I'm going to go back to my problem here, but I am working with 3.182. Cycle through my many faces, great. 3.182. I'm going to type this into my calculator, once with the minus, once with the plus. And out of curiosity, I'm actually going to type in the MO on its own here because I'm really curious how much it varies. So I think cats weigh 10 pounds on average, give or take whatever this monstrous number is going to be. Give or take 2.598. If I wanted to improve my precision in this problem, and note I'm saying precision and not accuracy because I am 95% confident in this thing, but if I want to have a little bit tighter of an interval, I might want to consider having more than 4 as my sample size. But I'm going to type this in once with the minus, and once with the plus, and I'll see what I get. Plus is easier, 10 plus that number is just going to give me 12.598. If I do this with the minus, I end up getting 7.402 units on this, pounds. As with any interval, when I do this, I should end this with a sentence. So my interval in this case would look like we are, and I'm saying we because we got to do this together, 95% confident, ... that the true average weight of cats is somewhere between 7.402 pounds all the way up to 12.598 pounds. I want to just do a quick overview of this problem. In order to create this interval, I had to find my average and standard deviation. If you know some shortcut to do that using Excel or your calculator or GeoGebra, go for it. I am not grading this part here. This is all just scratch work. So if you have a fast way of finding these values using technology, make that happen. This is the new part, and this is only like 2 steps. I plug in my average, I plug in my critical value, my standard deviation, and my sample size, and then I finish the problem almost as soon as I start it when I'm actually looking at the 244 stuff instead of just that review of 243 material. Big bang for the buck. I'm making conclusions about populations based off a sample. I love being able to do that. Next lesson, I'm going to learn how to test claims about populations. It was great working with you here today. I look forward to doing another lesson soon.